So there are four types of chemical reactions, and we've already looked at double displacement. So what we're interested in this presentation is we're going to be finding singular atoms. So here's what happens. Compounds are going to be either aqueous or solid, and elements can exist in two different ways. So the first one is if we just have a singular atom by itself. So for example, you could have silver by itself, it would be in the solid state. Or maybe calcium, that would be in the solid state. Or iron in the solid state. Or gold, mobilium, these are all metals, and when they're by themselves, they're in the solid state. Now the nonmetals as well too. Phosphorus is a solid, carbon's a solid, and then our group 8 gases are gases. So argon and xenon would be gases. So if an atom's by itself, most of the time it's just going to be a singular atom. But there's another situation. They could also be a diatomic gas, and there are 7 diatomic gases. So we write them like this, and we call them the Haber-Finkel gases, and they each have a little 2 here. So these are diatomic gases, di meaning 2, so these are gases that have to a particular atom. And since they're gases, we're going to put a little G beside them for gas. And if you had to name them, you'd say hydrogen gas and oxygen gas and so on. So we have to be wary through this next set of equations if things are by themselves or if they're a diatomic gas, and then we'll know our state. So first one we'll look at is decomposition, and quick definition of that would be a compound that breaks up into its atoms. So decomposition would be like something decomposing. It breaks down. Now if you had compound AB, it would in fact break up into A plus B, and what we'd have to consider though is are A and B on the diatomic gas list, and if so we might have to add a little 2 to their formula. So let's give this a try here. So we want to create a balanced chemical equation, and we're going to name everything and include the states. So we've got our first one, Al2S3, and it is in the solid state. So the steps would be, you would break up the compound into its 2 atoms. You would consider if either of them are on the diatomic gas list, which neither of these are. So that would mean that they are both in the solid state. And then you would go ahead and balance this one. So if we've got 2 aluminums on this side, of course we want to put a 2 in front of that to balance. And then we have 3 sulfurs here, so we'll want to put a 3 in front of that. And then some names. Aluminum sulfide, aluminum metal, and then just sulfur. So let's take a look at a couple more examples here though. Same instruction. And here's some steps to follow if you need a little more assistance here. So step 1 is you write the 2 atoms. So we've got aluminum chloride here, and clearly the 2 atoms would be aluminum and chlorine. So we'll write aluminum plus Cl. Step 2 is check the diatomic gas list. There it is on the side, and of course we've got Cl2 on it, so we're going to go back and add a little 2 next to Cl. Then we can determine our states. So aluminum's all by itself, and it's a singular atom, so it's going to be in the solid form. And of course, chlorine was a gas, so it's a gas. Nextly, we shall balance. You can start anywhere you want. Usually I like to balance out my chlorines in this situation because I've got 3 chlorines on this side, and I've got 2 on that side. And 3 times 2 would be 6. I want to get 6 chlorines on either side. So what value, what number do we want to put, what coefficient do we want to put in front of the aluminum chloride here? We want to put a 2, because that 2 multiplies against the 3, giving us 6 chlorines. And over on the other side, we'll put a 3, because 3 times 2 gives us 6 chlorines as well. Now let's consider that this 2 also applies to the aluminum, so we're going to need to put something in front of this aluminum, and that's going to be a 2. Our next step is we're just going to go ahead and name everything. And so we've got aluminum chloride, we have aluminum metal, and we have chlorine gas. Let's try this one more time here. Feel free to pause the video and fill this in if you wish. If I was going to do this one, I would first write my 2 atoms, sulfur plus oxygen. Next thing I would do would be to check my diatomic gas list. And of course, oxygen's on the list, so we'll add a little 2 there. Then we're going to determine our states. Sulfur is a singular atom. It's going to be a solid. Oxygen is, of course, a gas. It's on the gas list. And then we're going to need to balance this one. And there's probably a couple of places you could start. With this one, we've got 5 oxygens and 2 oxygens. So 5 times 2 is 10. So we really want to get 10 oxygens on either side. So we got to ask ourselves, what do we need to put in front of our compound here to give us 10 oxygens? We need a 2. 2 times 5 gives us 10 oxygens. Then over to this side here, a 5. 5 times 2 gives us 10 as well. And again, let's not forget that this 2 also applies to multiplying against the sulfurs there, so it looks like we're going to need a 6. And then finally, our last step will, of course, be to name everything. Now, this one here is actually a covalent compound, so we do have to say trisulfur and pentaoxide. We need some prefixes. And then we've got sulfur by itself and oxygen gas. So here's our definition of decomposition. It's the compound breaking up into its atoms, but there's maybe a more complicated way of doing this as well, because they don't necessarily need to break up into their atoms. They could also break up into 2 smaller compounds. Now here's an example here. We've got carbonic acid, and through experimentation, it's been discovered that this breaks up into water plus carbon dioxide. There's really no way for you to physically know that these were the 2 products unless you did an experiment and knew what the result was going to be, and then you simply go ahead and memorize this. So really, when it comes to decomposition of a compound into smaller compounds, you need to memorize what the 2 or 3 products are going to be. That's the only way to do it. So on to our next one is synthesis, and this is just the exact opposite of decomposition. So this is going to be a reaction where 2 atoms are combining to make a compound. So we've got atom A plus atom B combining to make, and I do have a note here that the compound AB is of course formed using the crossover method. So in my simple example here, it's just compound AB. But of course, if this were a little more complex, there may be some charges here. You may need to cross over and get a new formula. But for this one, it's just going to be A plus B gives us AB. So let's go ahead and do our balanced equation here. So in this one, we've got to have sodium that's in the solid state plus sulfur that's in the solid state. So all we're going to do is we're going to put sodium together with sulfur. Well, how do we get this? Well, let's consider that sodium had a charge of +1 and sulfur has a charge of -2. So really we're crossing these over. So how many sodiums are we going to get? Well, we're going to get 2 comes down. We get 2 sodiums. And then how many sulfurs are we going to get? Oh, we look up here and it's a 1, so we got 1. So there is actually our formula. So we've done a crossover here. Our next step would be to determine its state, and this is where we would look to the periodic table, the rules that I have outlined on the periodic table for my students, the solubility rules. If you happen to be watching this video and you need to look at them, you'll find out that sulfides are in the aqueous state when combined with sodium. And of course, there's always a little bit of balancing too. We've got 2 sodiums here, so we'll put a 2 in front to give us 2 sodiums. That should balance that. We've got sodium metal, sulfur, and sodium sulfide. So that is a synthesis reaction where you have 2 atoms combining to make a compound. Here's another example where we've got lithium plus chlorine gas. Again, what we want to do is we're going to say, okay, we've got lithium combining with chlorine here, and you look their charges up. They each have charges of 1. So that means that our formula for lithium chloride is just LiCl. Once we've got that down, then we go ahead and we say, okay, we've got a 2 here for chlorine, so we better put a, also I forgot the states. Look that one up. That would be a halide, which is aqueous. Then we get onto our balancing where we have 2 chlorines and 2 chlorines, and that also applies to multiplied against the lithium. So put a 2 in front of the lithium, and then we'll name everything lithium metal, chlorine gas, and lithium chloride. Onto our 4th and final type of reaction, which is a single displacement. So a single atom is going to react with a compound. Now we need to consider that the atom that's by itself might actually be a metal or a non-metal, which means we actually have 2 cases here. So we've got case 1, which is metals, or cations might be a better way to say it. And so in this case, what we're talking about here is we're talking about A is a A is a metal, and what it's going to do is it's going to switch places with B, because B is in the position where the metal or cation would be. So you liberate B, and then you end up with compound AC. Now there's a second outcome, of course, is that this time A is a non-metal, or an anion, And so, in fact, this time it's actually going to switch places with C. So you actually get C by itself and then compound Ba. So you need to be wary of what the singular lone atom is. Is it a metal? Is it a non-metal? Because they're going to do different things. So looking at this example here, we've got sodium. So if you go to your periodic table and you look it up, sodium's a metal. So it's going to switch place with the calcium, meaning calcium will end up by itself. And then the other compound is going to be made of sodium and chlorine, each of which have charges of 1. So our formula is just NaCl. Next, we're going to do our states. Calcium is a solid because it's not on the diatomic gas list, so it has to be a solid. And then sodium chloride is going to be aqueous. It will dissolve in water. Check your solubility rules. And then the last thing is to do some balancing. So if I was looking at this one, I'd say, okay, 2 chlorines here. I better put a 2 in front. That gives me 2 chlorines. And then 2 sodiums, 2 sodiums. And your last step will be to name everything. Sodium metal, calcium chloride, calcium metal, and sodium chloride. Now, so that would be I guess you could call it a case 1, where we've got a metal. Now, this is one where we've got a non-metal. You need to recognize that bromine is a non-metal, so it is going to switch with the potassium. There's no, it's going to switch with the phosphorus. There's no way that bromine could switch with the potassium, because putting bromine and phosphorus together, it would be a covalent compound. We wouldn't know the charges. There wouldn't be any charges. You couldn't cross over. So in essence, the only thing that can happen here is the bromine switching with the phosphorus. So we get phosphorus by itself, and then we're going to get potassium and bromine. And again, consider that potassium has a charge of +1, and bromine has a charge of -1. So KBr should be our formula. Next, we'll think about the states here. Phosphorus is not a diatomic gas, so it's a solid. And Br is a halide, so it's an aqueous compound. Then onto our balancing, and there's lots of places you could start here. Looks like the first thing I thought of was, okay, I've got 2 bromines here, so I'm going to balance the bromines. I'll put a 2 in front. And then that gives us 2 potassiums. Then you'll note that we actually have 3 potassiums on this side. So this is one of those situations where it's like, okay, I got 2 on one side, 3 on the other side. I want to get 6 on both sides. So we actually have to do a little bit more extra work on this one, because now that gives us 6 potassiums. Well, back over to the other side here now, we got to correct what we did. We actually need a 6 in front of that. So now we have 6 potassiums on either side. But of course, now that's throwing the bromines out of whack, right? Because we have 6 bromines. So what should we put in front of here? We already have 2 bromines. You're probably thinking it's a 3, and you are correct. And then the last thing to balance would be we have 2 phosphoruses on this side. 2 phosphoruses there. Done. Bromine gas, potassium phosphide, phosphorus, and potassium bromide. And those are your types of reactions.